We're working on solutions still, and we just looked at how to calculate molarity, which was a review from chapter 4. You've also seen that capital M for molarity on some of the solutions in lab. So next we're going to remember, again from chapter 4, how to do dilution calculations. So dilution is like when you buy concentrated, say, juice at the store, and then you add water to it, it becomes more diluted. And this was the equation that we had used for that. C1V1, C stood for concentration, V stood for volume, and then concentration and volume. So we should in these problems see 2 concentrations and 2 volumes by the time it's all done. So if we take this solution here, so we're going to keep using this data, and we're going to dilute it to 100 mils, so go from 50 mils to 100. We want to think about, first just think about it conceptually. So if I dilute it, I'm adding water to it, right? Just like you would add water to concentrated juice. So if I add water to it, is it gonna be more concentrated or less? Should come up with less. Less if you can think about taste. If something's more diluted, it tastes more watery. So my concentration is going to decrease and my volume will have increased. That's our conceptual piece. Now it says calculate the new concentration. All right, so these 2 numbers obviously go together and we actually have a molarity now here. So I could say that C1 is this 0.9011 molarity. V1 is this 50 mils. C2 is what we don't know, so we're working on that, and V2 is going to be 100 mils. Notice all the significant figures here. This would probably be done going from a small volumetric flask to a larger volumetric flask. That's how we get that many significant figures usually in one of our volume measurements. So in these flasks, remember, it would be as if I had 1 solute and still 1 solute. All that's changing is the volume of solution. So if I look at my equation here, I'm going to be solving for C2. So if I rearrange, I get C1V1 divided by V2 is equal to C2. So I want to plug in now C1 0.9011 molarity times the volume. Now all that really matters on my volumes is that they're in the same unit. Same with concentration. This doesn't have to just work with molarity. I can use it with all kinds of concentrations. You just have to have units that match. So 0.9011 molarity times 50 mils, and then divided by V2, which is that 100 mils. When I work that out, punch it into your calculator, you get 0.4505. Mils cancel, and so this should be in units of molarity. Go back to what my solute was, because I want to write that down. This is calcium chloride, and this is important because when you go into lab, you've got all kinds of different solutes, and even just by the end of this chapter, we're going to have a bunch of different solutes as well. So you want to say, what solution are you talking about here? And then check it. Make sure that what we thought should happen happened. So the volume increased, right? And the concentration should have decreased. And sure enough, it decreased. What happened was I doubled the volume. And as a result, I have half the concentration, right? 0.45 is half of the 0.9 that I started with. So that would be the result of my dilution. All right, so you want to be able to do those problems as well. And then we have one new type of problem that we haven't seen before, molality. And molality is going to be sounding a lot like molarity, right? Molarity, though, is temperature dependent, we say. And that's because the volume is going to change if we change the temperature. So if we have something that's occurring over a wide range of temperatures, or we need to get that temperature variable out of there, we use instead kilograms of solvent, and this is not temperature dependent. So that's the value of using molality instead of molarity. And the symbol for molality is going to be a lowercase script m, so that's kind of my handwriting M there for molality. So I've just got new numbers for you here. Calculate the molality of a solution if 5 grams of calcium chloride were dissolved in 4.5 kilograms of water. Shouldn't say were used. All right, so molality is moles over kilograms of solvent. We already did this calculation, right? 5 grams of calcium chloride was this many moles here. So I'm just going to bring that number down with 4 significant figures. And it needs to be kilograms of solvent, so 4.5 kilograms of water. Not a lot of sig figs there, or less sig figs, right? So that's going to limit our significant figures. When I do that calculation, I get 0.100, and I'm going to write that script M and say what the solvent, or sorry, the solute is, the calcium chloride. So this is the molality of a different solution, more water here than what I had in these situations. So you should be able to calculate molality as well. All right, so be able to do your metric conversions, calculate molarity, do dilutions, calculate molality, and that will take us to the next page, which is going to be working on a whole bunch of molarity calculations. You want to be really strong on these and able to work them. So before you come to class, please do this top one and give this one a try. So we'll start with questions on those and then work more of these and the next pages of problems in class also.